So I'm Elmar Peters. I used to be a member of Solar Team Twente in the Netherlands, and we participated in Australia. And then I've worked on a special system to get more energy out of the solar array for them. And then after that, I started my own business and I sell maximum power point trackers to get solar energy out of arrays. And today I'm presenting about, oh no, shade on my array. So as everyone knows, let's see. How can I go? The outline for today, I'll show some examples of solar cars and how shade and curvature of the array impacts how the array gets in. I'll show like some simple modeling of solar cells to see what shade and curvature of the array means electrically. And then I'll talk about some solutions or tricks to reduce the negative impact of mismatches and shade on your array. And let's see. Examples. So one thing that commonly happens with solar cars is that you want to make like an aerodynamic solar car, which basically means that you usually have a canopy on the solar car, and when the sun is low enough, that generates a shadow on your solar array. Another thing that you can see here is that because of the aerodynamics, like the car has a certain shape, which is not flat, and that causes every solar cell to be in a different angle with respect to another solar cell. And then because of that, there's a different amount of irradiation on every single solar cell, which causes some problems when you put them together in groups. Let's see, I have some more pictures. Well, this is probably, well, they don't care about that sun anymore, but this is a canopy causing shade on the array as well. And then this is a solar car with the canopy in the side. That's an advantage because if you have the canopy in the middle, you get shade on your array both in the morning and the evening when the sun is low. Like that's like, I'm not sure if it's the same for the American solar channels, but in Australia they drive from north to south. So you have shade on your array both in the evenings and in the mornings. And yeah, having this canopy on the side is an advantage because then you only have shade one time of the day instead of two. Let's see. What else? Well, this is another example of like a car with a super curved array. And that causes a mismatch in irradiation because the sun will have more light on the array that's more perpendicular to the direction of the sun. So some simple solutions, like if you would just put your array on top, like you would not have any shade, and if you would make it flat. But of course, for most solar cars, that's not ideal because you also want to have good aerodynamics. Something else. Oh wait, Michigan, like on some of their cars, they don't put that much solar arrays next to the canopy, so you don't have the shade issue, which is a good solution electrically, but it might make your car a little bit bigger.
For reference, I'm pretty sure Electrum was about 2 inches wider than Novum, specifically to move the solar cells behind the canopy.
Yeah, but it's but electrically you can probably get more power, so that might be worth it. This is like a picture of the Twente car that I was an advisor for. And one thing we did here is we choose to cut the cells next to the canopy. So you have smaller solar cells, which helps because that way you can make the groups, the solar strings that you connect to a single MPPT smaller. So the reason we did this is because of the canopy shade. Like smaller cells make smaller groups, make grouping less inefficient. Grouping is something I'm going to explain now. So if you have a solar cell, it's basically a diode with a current source in parallel. And the amount of current the current source provides is, let's see, is more when there's more sun. Like it's linearly dependent on the amount of irradiation on the solar cell. This is a graph from the SunPower data sheet. So you can see that there are IV curves for the different solar cells. And when there's less irradiation, there's less current. And you can see that the voltage, the maximum power point voltage of the cells is relatively independent on the amount of irradiation. And what you want to try to do is get the most power out of the solar cell. So you want to have the biggest product between voltage and current. So you always try to like regulate the voltage to be like, in this case, maybe like 0.55 volt. So you're on the maximum product of current and voltage, I think. Yeah, this is how a maximum power point tracker works. So the blue graph is the let's see, the voltage on the y-axis and the current on the x-axis, and the orange curve is a power curve with the power on the x-axis, the power on the y-axis, and the voltage on the x-axis. And you can see that maximum power, like the MPPT tries to like stay on the maximum power point. That's the whole goal of what the maximum power point tracker does. But it gets more difficult if you have combinations of cells that have a different irradiance. So in this picture, like I just put two values on there. Like if the sun is somewhat perpendicular on the array, you got like 800 watt per square meter. If it's not pointed at all, you might get like around 500 watt per square meter. And what happens is that you have two different solar arrays with two different irradiance values. And you can see here that the maximum power point current for the solar cell that gets less light is lower. So you have two different optimums, like the solar cell on the left wants a higher current than the solar cell on the right. And what you typically do when you make solar arrays and you connect them to an MPPT is that you put multiple cells in series. So I made a drawing of that here. So here you have two different cells in series with two different irradiances. And what happens when you put two cells in series is that you add the voltages, and the current through both cells becomes the same because they're connected in series. So this graph on the left is the IV curves of both cells stacked on top of each other because you put, so the voltages add up. And now the maximum power point tracker can only regulate on a single current. So if you regulate on IMPP, the green IMPP, the maximum power point for the green solar cell, that might be optimal for getting energy out of the bottom cell. But as you can see for the top cell pointed in yellow, drawn in yellow, you're underutilizing the amount of power you're getting out of it because you're not on this maximum power point, but you're slightly more to the left, which gives you a little bit of extra voltage, but way less current. So your maximum power is going to be less. So on the right, I drew the power curves versus current for both cells. And then if you add those up, you get like this curve with like two different maximum power points, like two different optimums. And none of them utilizes both cells. Like with this maximum power point, you're close to utilizing the bottom cell perfectly, but you're nowhere near utilizing the top cell perfectly. And on this, when you're on the maximum power point of the yellow graph or the orange graph, you're basically not getting anything out of the green cell, the bottom one, because it has, at those higher currents, it has 0 voltage. And this is already assuming it has a bypass diode, because if it doesn't have a bypass diode, you cannot even regulate this current, or you might get a damage in your cell. And this is how, like, this is a picture of a IV curve and a power voltage curve of a solar array, where you gradually get less shade. Yeah, so this is the point where, so like in the beginning of the animation, you have a lot of shade on your array, and then it slowly, the shade disappears and you get a lot of sun. And this is actually an animation of where the maximum power point tracker is doing a pretty good job. In practice, not all maximum power point trackers deal well with maximum power point tracking with IV curves like this, because you have 2 different local maximas, and sometimes the maximum power point tracker gets stuck on the wrong one. Like, you see that for an instant in the beginning of the animation, it's not always on the highest top. Like, you want to make sure it's on the highest one. So that happens to like all kinds of teams. I have like a little video that I found on YouTube. It's, you can, well, I'll explain it later. Right. There should be no audio anymore now. All right. Okay, so that was a video of Team Vattenfall in Africa. And what they were saying is, yeah, today we almost didn't get any sun until the end of the day, because there were some trees on the side of the road that sometimes cast a little bit of shade. And then because of that, the MPPT got like stuck on a really low current that's optimum for shaded arrays. But then it wasn't able to regulate to the right optimum when there was no shade anymore. Like maximum power point trackers get really confused with shaded arrays, basically. And what they're saying is that they like programmed in a new maximum power point tracking algorithm overnight to like somehow prevent this a little bit. Like my main message here is like maximum power point tracker get really confused with shaded arrays. Like, they have no clue where to actually track. Like, and it's difficult. Let's see as well, because it cannot, like, the maximum power point tracker only sees the voltage and the current of the point where it's tracking. So right now it cannot see the other point. Like, it has to do a global sweep or something like that, which you don't want to do too often, because then while you're doing that, you don't get the maximum amount of energy you want. Let's see. So one thing you have to do when you have like arrays that could get partially shaded is add diodes. Diodes are both to get more power out of your array, but also to avoid damaging the solar array. So what happens is, if you have one solar array and there's shade on there, you basically can choose to regulate to the current that's optimum for the other array, so you at least get the full power out of those. But then you need some way to bypass that current. So that's why you use diodes. For example, if you don't have a diode, you try to run the array at the current that's optimum for the non-shaded arrays. Like, what could happen is that you get like a negative voltage over the array and you force current through it, which basically means you dissipate some power from the non-shaded arrays in the shaded array, and it can get really hot and damage the array even if you do a bad job in regulating this. So that's why you have diodes. And like, here's just an example of like an array that consists of 4 solar cells, and the top one has 4 diodes as well. And what you can see here, the first two cells are shaded. So what happens is that the first diode conducts the current to bypass the first cell, and the second diode is there to bypass the second cell. And those diodes actually dissipate some energy because of their voltage drop. But it's worth it because you get more energy out of the non-shaded cells because you can run them at their optimal current. So with these solar cells, you're getting no energy out of the solar cell and you're dissipating some energy in the diode. And some teams are like, hey, why? Let's just give every solar cell a diode. That might not be optimal either because the more diodes you have, the more in series, the more losses the diodes create. So ideally you would just bypass all the shaded cells with a single diode, but then you never really know where the shadow is. So in this example, you would rather have like the bottom scenario because your bypass current only has to go through one diode, which is 1 times diode loss. But for example, if the two middle cells are shaded, you want to have the diode just across those. And to accompany for all the different scenarios you can get, like something like this might even be ideal. And you can even add like an extra diode to like bypass just the middle two cells. So that gets really complicated with the diodes, especially if you have lossy diodes. So what people started doing is use smart diodes, so you don't have the voltage drop because the diodes when they conduct, and like the first picture of a smart diode is something I found in 2006. Like it was like some handmade smart pass diode. Nowadays, there are companies like Texas Instruments that make like little chips that look like a normal diode, but then inside of those chips, there's actually like a switch that can bypass the normal diode. So you have like no voltage drop across the diode when it's on. So how those integrated diodes work is, well, they use the voltage drop across the diode when it's conducting to like charge a little capacitor with a charge pump. And then they turn on like a MOSFET that's in parallel to the diode. So this way you don't have diode losses in your bypass diodes. Let's see. So that MOSFET doesn't stay on forever. So what sometimes happens with those smart bypass diodes, that they turn off the switch again, and then the diode starts conducting, and then while that happens, it charges the capacitor, and then it turns on the FET again. So with smart bypass diodes like this, like you have some switching behavior on the switch, like it's not on all the time, but only sometimes. And what also happens is that once you want the diode to turn off, sometimes the switch stays on while you don't want it. It just sometimes samples to see if it should be on or not. And that could confuse the tracking algorithm of the maximum power point tracker as well. So you have to be careful with that. Like in the datasheet, it usually mentions how often it looks to see if it should turn the switch on or off. Let's see. So this is about the diodes. So like shaded arrays are not ideal, then the way of dealing with them. But diodes is not ideal either, because when you have two shaded arrays, there's still some potential energy you would be able to get out of it. But by bypassing by diodes, you're just wasting that energy. But also if you don't have the diodes, you cannot, like it's just annoying to have like two cells with different maximum power point currency, because you can never run both of them at their optimum current. So what you can do is make more groups, smaller groups. So ideally you have, like if you could just connect the maximum power point tracker to every single solar cell, you would not have matching issues. Okay, so let's do that. But then, and connect that to an MPPT. And it turns out the MPPT losses increase if you connect less solar cells to them. So this is a graph of MPPT efficiencies for different voltages of the array. So like a voltage of a solar cell is around 0.6 volt in their maximum power point. So this below graph is like 50 solar cells in series to get 30 volt. And you can see the more cells you put in series, the more efficient the MPPT gets. Actually, I have another graph that shows only the losses in the maximum power point tracker. And you can basically see that the losses are not even that dependent on the solar cell voltage you connect to it. The efficiency is because, well, if you connect double the amount of solar cells, yeah, you have a similar amount of losses. So the losses in percent, like, let's see, like basically connecting like double the amount of solar cells to a maximum power point tracker gives you approximately the same losses. So the losses in percent get like half. So you would like maximum power point wise, you would like connect as many like solar cells to an MPPT as possible, because then you get the highest efficiency here. But like grouping loss wise, you would not want to connect more cells in series, because then you get the grouping issues. So there are other solutions as well. A lot of Japanese teams, they put MPPTs in series. This is like an example of an MPPT Nomura is selling from Japan. And what you can do with those MPPTs is connect the output of the MPPT in series. So on the left is a picture of solar cells in series connected to a single MPPT. And what you do with the Nomura MPPTs, you can connect the output of the MPPTs in series. And what this allows you to do is track the maximum power points of individual small groups instead of grouping everything together. This works well for curved arrays when there are like small differences in the input. So here you can see like the amount of power you would get from like small groups on a curved array. This does not work well with shaded arrays, and I can demonstrate that. I would like to draw, like, let's see. So how an maximum power point tracker works is that you usually have a boost converter that you connect to a solar cell. So a boost converter looks like this. And on the output, you usually connect your battery, or like there's usually a capacitor. And then you would connect the battery. So this is how an MPPT looks. It's a boost converter. And the way a boost converter works is that it boosts the voltage. So you can have like a solar cell on the input, which maybe is like 80 volt. And then you boost it to a battery that's maybe like 120 volt. That works. Like a constraint of a maximum power point tracker is that the input voltage should always be lower than the output voltage. So with the series MPPTs, you would, of the Nomura, based on a boost converter as well. But if like, and I'm gonna draw that like a second boost converter. So what you could do, you split the array in two groups of two MPPTs you put in series. And if they have similar, if you just put it in half, you would just have two groups of 40 volts instead of one of 80. And then you would connect the battery to the combination of the two outputs. Let's see. And then if they have equal power in the input, so maybe it's 40 volts, 10 amps. And this is also 40 volts, 10 amps. So they're both 400 watts. You would also have equal voltage ratios on the output. So this point would be 60 volts. And then you have the same boost ratio for the MPPTs compared to the example where you had one MPPT. So like 60 divided by 40 is 1.5. Earlier we had 120 divided by 80 is also 1.5. So this theoretically they operate at the same boost factor. But now let's say you get a little bit of shade. Or no, let's first like look at the curvature. So let's say it's curved, and this top MPPT gets like 10% less. So then, because there's it is curved a little bit and it's a little bit not as pointed to the sun as good, so it gets like 10% less energy. So the current would be 10 times less. Is 9 amps. Okay, now this intermediate voltage here in the output changes as well because they both have different powers and they both have the same current. So what happens now is, assuming that they are 100% efficient, is that you get 40 times 9 is 360 watts on this output. And 400 watts on this output. So they have different amounts of power generated for each MPPT, and the current through this output has to be this of this MPPT has to be the same as the output of this MPPT. So we can calculate the current by taking the total power, which is 400 plus 360 is 760 watts in total. And then the current you get on the output of an MPPT is 760 divided by 120 is equal to, let's see, let me check.
6.3.
6.3, thank you.
It's 6.3 repeating technically, but
can you with the calculator like then?
yeah, sure.
3 amps. Okay, and then based like, so now you know the total current. So now to get this intermediate voltage, you just do 400 divided by 6.3. So what would be 400 divided by 6.3?
63.2.
63.2 would be the output of this MPPT. And then for this series, and then the top one would be 360 divided by 6.3 amps.
Yeah, 56.8.
56.8. Okay, so this is an example of where series MPPTs work well, because 56.8 is still higher than 40, so that works well. And 63 is still within the operating range of the MPPT, hopefully. And it's higher than 40, so that's okay. What you have to be careful with when you put MPPTs in series is that this output voltage always has to be higher than the input voltage. And the maximum output voltage has to be lower than the maximum rating of the MPPT. So with small differences in the output current, this works well. But now let's say like one of the arrays gets shaded, then like a shaded array gets like, let's say maybe 20% of the irradiance. So then instead of 9 amps, it will be like 2 amps. And now we can run the numbers again. Let's see. Let me get rid of the old values. Oh wait, that one actually was still correct. Okay, so let's recalculate everything. The top MPPT now gets 2 times 40 is 80 watts. And then the bottom MPPT gets, well, it still gets 400 watts because nothing changed. So it's 40 times 10. Now the total power is 480 because it's 80 plus 400 watts. And now the total current through like both outputs of both MPPTs and both into the battery is 480 divided by 120. What is 4 amps? So in this example, the output voltage of the lower MPPT would be like 400 divided by 4 is 100 volts. But the output voltage of the top MPPT would be 80 divided by 4 amps is 20 volts. So this does not work. This is like an example of why like series boost MPPTs with shaded arrays are not always a good idea, because this 20 is lower than this 40. So this like a boost converter cannot operate like this. The output voltage always has to be higher than the input voltage. So what it's going to do is say like, I'm not going to work with those values. So instead, it will just go to its maximum, like to its minimum output. So it will go to 40 volts. So this MPPT just becomes a diode basically, because it's not within its operating range. So then the output voltage becomes 40 volts. We'll still get the 2 amps because now it's basically just the solar array connected to the output, and I'm assuming the diode is ideal. Okay, so now the current output of the bottom MPPT has to be the same as the top because they're placed in series, so it's 2 amps. Voltage is already defined as well. The battery voltage minus the voltage of the top MPPT, so it's 120 minus 40 is 80 volts. 80 volts. So that's 160 watts, and now we have 160 watts on the input as well because it's same as the output. Let's say the voltage of the cell stays approximately equal to the maximum power point voltage because it doesn't change much if you reduce the current. Then you only get 4 amps instead of 10 on this solar cell. So this shows that like it's really not a good idea to have boost converters placed with their output in series with shaded arrays. Like it works well for the curvature, but not for the shade. Are there any like questions already about how series connected MPPTs work now? None at all? Okay. Like Tokai last year during the World Solar Challenge in 2019 solved this by making buck boost converters that they placed in series. So with buck boost converters, the input and the output, like the output can be either higher or lower than the input. That worked better than the boost, like the series placed boost converter they told me, but it still had like some challenges with that. So series MPPTs, like the summary is, it works well for solving little differences in cells, but it doesn't work well. Like it might actually work worse than bypass diodes when you have shaded arrays. That's an important message. Something that does work that we tried with Twente is decentralized maximum power point trackers. Like we tried it for the first time in 2015 and got the innovation award for it. Basically, what a decentralized maximum power point tracker does is, this is not the circuit of the thing Twente used, but something I got from the internet, is that it has multiple solar cells on the input that are all connected in series to a single MPPT. So this MPPT can still run at a high voltage at which it's efficient. And then to compensate the differences between the cells, it has a decentralized maximum power point tracking circuit that can transfer energy between cells. And that way it will track the individual maximum power point of each individual like substring. And the currents through the MPPT circuit are usually low, so the losses in the DMPPT circuit are low compared to the MPPT if you design it well. And you can still run the maximum power point tracker on an efficient operating point where the voltage is high. I wanted to give like a simple like explanation of how DMPPT tracking works. So let's see. So I'd like to make it as simple as possible. We have two solar cells. Wait, I don't want to have red solar cells. Let's make an example with two solar cells, or so like it's a combination of a couple of cells, but like with two groups. Let's see. Let's both connect them to a single MPPT. So if we have the MPPTs, we have a different way of solving the grouping issues. So we can just pick our voltage of the array to be as high as possible for the MPPT. So let's see, usually you would just pick, well, maybe like 100 volts. Because that's like, you'll probably pick like something close to your minimum battery voltage. Then you have like a single MPPT. PT that you connect to your battery. And if you connect it like this and design the input of the MPPT to be as high as possible, you get your highest MPPT efficiency. Because we saw earlier that efficiency of the MPPT is higher at higher voltages. So with the best MPPT I make, which is, so as far as I know, the most efficient one available, you can get efficiencies like if you boost a 100 volt array to 120 volt battery voltages, you can get efficiency as high as 99.6% efficient of the MPPT. But now you need a way to deal with your mismatch, right? Because you might still have some curvature in your array. So let's say you have like a curvature in your array that causes like one of the sections to only cause like 8 amps of current, and like the one that's like directed to the sun a little bit better, 10 amps of current, and they're both at 50 volts. You cannot get the full utilize your solar array very well, because you either run the entire string at 8 amps, which causes you to lose like 10 minus 8 is 2. You get like 10 amps less out of the bottom array, so section, which is like a 100 watt loss, because 2 amps times 50 is 100 watt. Like that's an issue. And the alternative is to run it at 10 amps, but then I would have to bypass this top array with a diode. And even if you take like a smart bypass diode, which is ideal on a 0 volt drop, you would waste all the energy generated by the top array. You would waste like 8 amps times 50. You would waste 400 watts. Ideally, so with bypass diodes, you would be able to get 0 watt out of the top array, 10 amps times 50, 500 watt out of the bottom array. That's if you use the bypass diode. If you don't use the bypass diode and you run it at 8 amps, like with small differences, you usually don't use you don't want to activate the bypass diode. Now you get like 8 amps times 50 plus 8 amps times 50 is 400 plus 400 is 400 watt out of both arrays. So no bypass. Well, no bypass. Gets 400 watt out of the top array and 400 watt out of the bottom array, which is not ideal either. Like ideally, but so far there's no way to do this yet. You get 8 amps and 50 volt out of the top array because that's the maximum power point, which is 400 watts. And ideally, you get 500 watts out of the bottom solar cell, which is 10 amps times 50 volt is 500 watts. So in the ideal scenario, you would like to get 900 watts out of your solar array. By using a bypass diode, which is in this scenario not an optimum maximum power point, you get like 500 watts out of your array. And by running the array at like 8 amps, which is ideal for the top one, but gets you less power out of the bottom cell, you get 800 watts out of the array. So the bypass diode scenario is possible, but not desired. Like the other maximum power point is also not desired because it's 800 watt and you would ideally get 900. So what you would like to do, what the decentralized system can do is basically it subtracts 1 amp from this cell. Let's see. So you put some circuit, some black box that you connect across both cells. Black box. Let's call DMPPT. And black box. And what you want this box to do is basically subtract 1 amp from the bottom cell. So this would be both 1 amp. And then you want to add that 1 amp to the top cell. So you want to like, there should be some converter in that black box that subtracts some power from the bottom cell and adds it to the top cell. And now the total string current becomes 1 amp plus 8 amp is 9 ampere. Because we have the 8 amp of the solar cell and we have some parallel circuit, which is a DMPPT that adds 1 amp. And then the current through the bottom cell is originally 10 amp, but then we subtract 1 amp that goes into the DMPPT. So now the sum current here becomes 10 minus 1 is also 9 amp. And if this all works well, we get 9 amp in total, and the voltage is 100 volt in total. So we get 9 amp times 50 out of the top cell and 9 times 50 out of the bottom cell. We basically get like all the power out of the solar arrays now. Like the combination of the solar cell power and the added DMPPT power here is 500 watts. And the combination of the added power of the DMPPT and the solar cell here is also 500 watts. Which of course is 400 watt of the solar array and 100 watt that's get added through the DMPPT. And here it's like, I made an error. It should be 450 for both. So what we do is we 450. Yeah. So, but at the top one we get 400 watts of the solar cell, and we get 50 watts that's coming out of the DMPPT. So it's 450 watts. Here we have 500 watts of the solar cell, but we subtract 50 watt that goes into the DMPPT. So you have 450 watts. And basically the power flow in the DMPPT is that it like transfers 50 watts of power from the bottom cell to the top cell. So this 450 is 400 plus 50. This one is 500 minus 50. And this way we run both solar cells at their optimum. This is in short how like, and then you get the ideal scenario where you get all the power out of the solar array. Does this make any sense to anyone already? Or are there questions so far?
Yeah, it does make sense, but what exactly does the DMPPT do to transfer those 50 watts?
So what's inside of the DMPPT box, basically? That's what I can go into now. Yeah. Before I go into that, are there any other questions about this circuit that's on the screen right now? Or any questions about maximum power point tracking or solar cells in general? Like everyone is muted. Okay, so let's go into what's in the DMPPT box. Maybe I can simplify it a little bit already. Like I'm gonna draw a little bit of a simpler box. Now that we know that what happens, like we can just make this into one wire. And let's see, and the current in this wire is, let's see. So we had two wires at about 1 amp and we add them together. So I think it becomes 2 amps now. We can check this because 2 amps, does that make sense? Because this current flows like this. And this, let me get the arrows right. So this is a donor, so the current goes like this to donate 1 amp. And this is a receiver, so the current goes into the cell, so that's like this, 1 amp. Oh shit, 1 amp. So there's 1 amp like floating like this, 1 amp floating like this. Yeah. So we basically have a box that has 2 amps here, 1 amp there, 1 amp there, and the voltage across like if we have terminal 1, 2, and 3, the voltage between terminal 1 and 2 is 50 volt because it's the same as the cell. The voltage between terminal 2 and 3 is 50 volt. Here, can I make a screenshot of this? Well, I'll just redraw it. So let's go to the next page. Next page. So the button to go to the next page overlaps with the zoom control bar. Let's see. No, that does not work. Yeah. No. I cannot fix this. Wait, let's see. Let me make the screen smaller. Go to the next. Okay, so now I'm just gonna draw the DMPPT box, which is the same as in the previous slide. So I'm just gonna copy it. So like the DMPPT box had the 3 terminals. This one was 2 amps in that direction. This one was 1 amp. And then this one was 1 amp. The voltage between, because can we go back? Yeah. So I basically draw the same. I basically drew the DMPPT with the currents at all the 3 terminals. And then I can add in the voltages. So this is 50 volts.
Hey, Elmar.
Oh, yo, someone is calling me. That maybe someone is watching. Let's see, because the terminal 2 had a voltage that was like 50 volts higher than terminal 3. Yo, Michael, ik was over terug. Ik ben aan het presenteren.
Oh, sorry.
Let's see. So the difference between terminal 2 and 3 was 50 volts that we saw earlier, right? And then the difference between terminal 2 and 1 was also 50 volts. So like, let's say terminal 1 is 50 plus 50 is 100 volts. So there has to be some kind of power converter inside here that makes it happen. Ian, can you already imagine what kind of converter could be in this DMPPT box? Is Ian still here because he asked the question?
I am. To be honest,
Ian?
I'm not particularly familiar with power converters, so I don't have a immediate guess.
So for example, what you can do, you can put like like an ideal transformer in between, right? Like, which does not exist, but it's like you can, if transformers would work for DC, you would just get like a transformer like this, where you combine this to that terminal, where you have like 1 amp running through this coil. Of course, like transformers don't work for DC, but like if they would, you would have a converter with 50 volts 1 amp on this side, and you would have like an output of 1 amp 50 volts on this side. Like this looks very much like you can almost make it like a flyback converter. Like so instead of so DC transformers don't exist, but what you can do is make, so like, does it make sense that if you have like a transformer that can transform DC to DC, you could have something like a circuit like is it any did it have a circuit like this put inside of the box? Could you imagine like if there would be a DC transformer that you could have a circuit like this inside of the box?
Yeah, that would make sense.
But then because you don't have DC transformers, you have to like put something around it to make it AC. So what flyback converters do usually have like a MOSFET switch here and a capacitor here. And then you have a rectifier here and a capacitor here. That would work. This is how a flyback converter looks like. Then you have like an isolated DC to DC transformer. Like maybe there are people that are better at drawing this than me. You just have like a flyback converter that can do this. Here it is. And a flyback converter has a DC voltage on the input and a DC voltage on the output. Well, you can look on the internet how flyback converters work. But this will not solve the issue yet because well, this will work for what we've drawn here, but let's say the position of the sun changes and the top one becomes 10 amps. Oh, well, I'm not going to change the drawing because it's too complicated. But let's say the top one becomes 10 amps and the bottom one becomes 8 amps. That would want you to this Jamboard. That would change the direction of the current because it has to work bidirectionally. So you cannot just do a one-directional flyback converter. It has to work both ways. So in some cases you want to have like a diode here instead of a switch. And in some cases you want to have a switch here instead of a diode. So you can just, well, now it's supposed to be a little bit symmetrical, like, and so you can make a flyback that's bidirectional. Maybe like you can see that because you can take this switch and put it on the bottom side and you have exactly the same thing on the left and the right. Maybe the internet, like if you want to learn more about flybacks, you can probably, or bidirectional flybacks, you can probably find something on the internet about that. Here, bidirectional flyback is just 2 switches and 2 diodes on both sides, which is basically like a DC to DC transformer that can have the current floating in either direction. This is like one example of a power converter that you could have inside of the DMPPT box. There's also simpler topologies. Let me clear the frame. You can also have like another DMPPT. You can implement it in a lot of different ways. So we have the same box again, 2 amps. What did we have? We had 1 amp. This was an arrow. So one thing you can do, so this is the DMPPT box again, which is supposed to be the same as the box in this picture. And we had 50 volts here. We have 100 volts here. 0 volt here. This actually looks a lot like a boost converter circuit as well that you can put inside. So you can put the boost converter we had earlier. You can make a boost converter that goes from 50 volt to 100 volt. That should make more sense to most people, I guess, because a lot of people are familiar with boost converters because that's what you use in your MPPT as well. So you can make a boost converter that boosts from 50 to 100 volts. That has, let's see, I think 2 amps on the input. And then because the power on the input is 2 amps times 50 volts is 100 watts, the voltage on the output is 100 volts, so the current on the output is 1 amp. Because it has equal power on the input and the output. Could you see this boost converter circuit working? And then you can put that inside of the box, like you just connect this here. And then you connect this here. And then, let's see, you can see that this current here is also 1 amp. Let's see, that was it. And the current on the input is 2 amps. And if you connect that together, you get 1 amp. And you can just put your boost converter in the box. So that like you can like there's so many different ways of like implementing this. But like now I've shown like a DMPPT, like the concept of a DMPPT, and then like an implementation with a bidirectional flyback, and an implementation with a boost converter. Again, this boost converter only works if this direction of the current of the 2 amp is positive. Let's see. But let's say you switch the 2 solar arrays because like one of them gets more sun than the other because the position of the sun changed, then the direction of all the currents change. And you can imagine that if the direction of the current change, the boost converter doesn't work anymore because it's unidirectional. But what you can do is like buck converters tend to work really well with currents that go in the other direction. So you would just change the switch for a diode and a diode for a switch. And voila. And then if you want both directions to work, you can just put both a switch and a diode here. So here you put a MOSFET switch. And here you put a diode. And now you can choose which switch to operate and which of them to operate as a diode. So now you basically made a bidirectional DC-DC converter. And then, of course, there are way more ways to implement the DMPPT. I think the picture I showed in my slide was even a different one. Let's see. This is like the first thing I found on Google when I was looking for DMPPT. And it's even a different circuit. I think what they're trying to do here is just transfer power from the total string to individual cells. But like you can learn more about DMPPTs by just Googling nowadays. Like back when we developed this with Twente in 2015, there wasn't much information about this on the internet, but I think nowadays there are so many different research papers, like here, comparison of DMPPT PV systems. If you just go to pictures, there's so many like different ways. DMPPT is a word that's used for different topologies. Even the series MPPTs that we discussed earlier is also like a form of a DMPPT system. It's just where you like DMPPT is any system where you track like maximum power voltages of subsections of your array. Does that make any sense? Or are there any questions so far? Like also we already spent an hour, so maybe people can like come up with some questions or feedback, or is there anything in particular people want to share or ask? Feel free, because I'm done with the main thing I wanted to tell. No questions at all? Not even Ian? Yeah.
Hey, Elmar, that was a great presentation. Definitely learned a lot here.
Mhm.
I was just
Thank you.
a little confused on, so you're talking about how the series MPPTs don't operate great under shade, if one's shaded and one's not. I was just curious if you had any advice as to how to string them together so they actually, do work efficiently.
Okay, yeah. So how can you make, to rephrase the question, how can you make like series MPPTs based on boost converters work without having the shading issues?
Right, exactly.
Okay. I can put the Jamboard up again. Let's see. So who is this? Zach Ken? From what what team are you from?
I'm from the University of Virginia team.
Virginia. Virginia University does a lot of research on power converters, right? Let's see. I'll get the Jamboard out. We see the Jamboard. So let's go to the. So this was the example that did not work well, right? And the reason it does not work well is because there's a big difference in the output voltages, right? Some ideas people have suggested is to make this work well but there are like a ton of ways to, like the thing that Tokai did is they just made buck boost converters. And if you have a buck boost converter, you are able to convert 40 volts to 20 volts on the output that we wanted to have here. But yeah, buck boost converters are less efficient than boost converters. So let's say you still have two boost converters. One thing that you can do is split your battery, like make a center tap on your battery. So instead of a 120 volt battery, we have two times 60 volts. And now they kind of, the top and the bottom MPPT kind of work independently from each other. And they can both operate with a boost factor of 1.5 because and they can both run at their maximum power point. Zach, are you still here? Can you see how this works? And can you also see any issues this would generate for your solar car system in general?
So I'm not Zach, admittedly, but the main thing I see is that you could end up where the like top and bottom halves of your battery have different like SOC essentially, or like different amounts of energy left in
different
them.
currents at which they charge in this scenario, right?
Yep.
So can we calculate that? So this one is like 2 amps times 40 volts is 80 amps. 80 amps divided, or 80 watts divided by 60 volts is, let's say 1.33 amps. And now the bottom battery half is charging with 400 watts, because 40 times 10 amps divided by 60 is 3.67 amps. Yeah. So like, I hope I did it right. So yeah, this is a
I
problem,
think it's
right?
6.67, but
Sorry?
you said 400 watts, right?
400 watts divided by 60 volts.
Yeah, that should be 6.67.
Yeah, you're probably correct. Like that's pretty far off. Yeah. Okay, so that's even worse, right?
Yep.
Okay, so this is what you don't want. What you can do is, let's see. Well, you can connect your like converter here that that transfers energy from your top half of the battery to the bottom half of the battery. But now you have like an extra converter again, right? Now you're basically doing the same thing that the MPPT system was doing, but then on the output of the MPPTs instead of the input of the MPPTs. So yeah, that's not ideal either, right? There is another thing I came up with recently that should work a little bit better. let's see. But it requires even more groups. Like, so this example gets worse. Let's say you have 4 solar cells or 4 groups in your solar array, or however you want to call it. Let's see. I'm not sure what values I have to put in to make it work. Let me think. Let's say 8 amps, like here, 8 amps here. So 3 out of 4 are normal, operating normally. 8 amps here. Maybe like I messed up the values, but like that's not gonna be pretty, but whatever. 2 amps here for shaded array, like a quarter of the energy for shaded array. That should be kind of near being realistic, right? Okay. And we still have our 120 volt battery. And now because we have smaller groups, I'm going to make them a little bit of a lower volt. Like I have no clue what's exactly realistic nowadays, but let's make them 40 volt each. All of them are 40 volt. 40 volt. 40 volt. So what's the power? Like 320 watts?
Yep.
For the big groups. And the other one, this one is 80. Let's see. So if we have the DMPPTs again, or the DMPPT, the boost converters, is that what we add? Like I'm not gonna draw the boost converters, I just make it like a box. Each box is like an MPPT or a boost converter or whatever. Like this. Now we have like the same as we had earlier. So now we have, so now the left, let's see. The left side is going to work well, right? Those 2 MPPTs in series, because they're both equal. So this voltage is going to be half of the battery voltage, just 60 volts. Because they're both equal. Here you have a power mismatch again, because the top one is 80 volts and the bottom one is 80 watts and the bottom one is 320 watts. So like we did this mathematics earlier, right? But like so the total power is going to be 400 watts. So the total current is going to be 400 divided by 120 is 3 amp something. 3 point. Like anyway, like it's gonna like mess up again because wait, let me just see. Like I'm just lost with the numbers in my head a little bit.
I think in theory it'll be 96 volts.
96 here.
I think.
And on the top one
Would they make 24?
Yeah, so that's not gonna work, right? Because 24 is lower than 40. So what we can do is we can interconnect the 2 intermediate points. And then this is not going to be 60 anymore. And this is not going to be 96 anymore, but it's going to be somewhere in between. Because now the top MPPTs to like, how can we make this more clear? Like I'm just going to interconnect them 2 times. 3 times. Then remove those interconnects. Is it still the same, right? But then, like, now the top 2 MPPTs together make 400 watts. Because 80 plus 320. And now the bottom ones are going to be like 320 plus 320 is 640. And now you can run the numbers again, and then the bottom voltage, the voltage in the intermediate point is going to be, let's see, I don't have a calculator here.
I think it's 73.8.
73 here?
0.8, yeah.
Let's just make it 70. Well, 74.
In that case, 74.
Yeah, and then the top one is going to be like 120 minus 74 is 46.
Yep.
Bang. 46 is higher than 40 volts, so this works. Does that make sense to you? Like, does it make sense to Zach, and does it make sense to anyone at all? Like, like it's
Yeah,
very
that
little
definitely
feedback
makes
with everyone on mute. Like,
Yeah, that definitely makes sense. Just got to
Yeah.
keep it higher than the input voltage.
yeah, and you can like, and we had like 2 examples of doing it now. One of them was like doing an intermediate tap on your battery. One of them was making like a converter that transfers energy from the top side to the bottom side of the battery, and one of them is just to have more non-shaded groups in parallel with the shaded groups, so that the shade doesn't make that much of an impact anymore on the average voltages. Yeah, and I think this is something Tokai did in 2011. I found like a circuit of them online, and they had basically they had like 5 MPPTs on the bottom and 4 MPPTs on the top or something that they paralleled. And then the bottom 5, one of them was like that one that got severely shaded. And that way they were even able to balance it a little bit better. I'm not able to find that picture anymore. They removed it. But like, I think to make sure that doesn't like MPPTs don't work in series like this by default. Like you have to do some testing or validating with your manufacturer of the MPPTs, or make your own MPPTs to make it work. Even with the Nomura MPPTs, like the ones that are intended for putting in series, I've done some measurements with them, and like the intermediate volts get really stable, and they all like interfere on each other. Like there's some control theory in your MPPT that you have to do well to make this work. Tokai managed to make it work last year with their buck boost converters that they put in series. Like, but like I was in a conversation with one of the guys from Tokai, but like it was hard to communicate because he didn't talk English that well. And like somehow they didn't seem super satisfied with the system, but they seemed more satisfied with it than the test they did with my MPPTs. So obviously it works for them. But I remember Coca Queen, like it's only Japanese teams seem to be doing stuff like this, because all the other teams like don't trust that it's gonna work.
I mean, also all of the like MPPT manufacturers that do this are really from Japan. So
Yeah,
I'm sure
like,
that plays a part.
Tokai has a professor that specializes on this, and he made MPPT specially for Tokai that they don't sell to anyone else. So, well, maybe they're willing to sell it, but nobody asked them. Like, and then Coca Queen, I think they tried something as well, but they didn't really succeed, and then they ended up going for like just my MPPT. Also, this makes more sense to do with like silicon arrays than with a gallium arsenide arrays. And Coca Queen has a gallium arsenide array, so maybe that has something to do with it.
I mean, gallium arsenide is also dead in terms of WSC now, and probably ASC 22 also kills it.
Yeah, nobody's doing it anymore. Is it dead in general? Because I already saw satellites that go up in the air with like silicon as well. Now that the launch costs are lower.
Not really sure. That might be a cost savings thing.
And
I mean, I guess that I don't know how expensive it is to put a giant gas array up there, but
then I saw like UAVs, like those little airplanes that wanted to save weight, and then they put gallium arsenide on there. But then I don't know, like a lot of gallium arsenide array businesses are going out of business nowadays. You only have like Azure space left now, right? Which makes the most efficient gallium arsenide cells. But like one of the German teams told me that solar car teams are like a significant stream of income now for Azure space, which makes gallium arsenide arrays.
oof.
Compared to like the revenue they get from like satellites and space, like solar car teams were significant in 2019. That's crazy.
And with WSC nixing the category, that probably hurts them a lot. Then in that case, that sucks.
Oh yeah, but they were just lucky last time.
All right, so I guess one thing that was sent in chat that I don't think you've answered. Tristan asked, "What efficiency did you achieve with the DMPPT?"
What efficient? Like, so Twente doesn't want me to tell that. Because they don't want me to share the exact designs or the exact efficiencies. But I can say something else that's interesting. Let's see. So let's say we have this example, right? With two 50-volt arrays put in series, making a 100-volt array, going through the MPPT, and then the MPPT Well, I said like if you get like a normal MPPT, like and you boost from 100 volts to like 120, it should be around 99, right? Like I have one that's ridiculous and is a little bit more efficient, but it should be around 99 with the average solar car MPPT that you can buy. If you go from 50 to 120 volt with a normal MPPT, it's usually around 98% efficient. Does that like make sense to you? Like is this realistic in your mind? Like for like a normal MPPT. So like if you have two groups with two MPPTs, each MPPT boosts from 50 to 120 volt, then it should be 98. If you combine them together and you connect a normal MPPT, you get around 99% efficiency with your MPPT. Okay. So now that we know typical MPPT efficiencies, we can see what the minimum efficiency of the DMPPT system should be to make it better than having two MPPTs. So let's see. The power going through, the total power going through the main MPPT here is 100. What was it? 50 volt times 8 amps times 2 is 800 watts. So you lose 8 watt in total. If you would make two MPPT groups, you would lose like 2 times 8 watt. So the energy you can, the power you're allowed to lose in your DMPPT is 8 watt or less. And if you manage to achieve that, you basically have a system that's more efficient than having two separate MPPTs. Does that make sense? That like this maximum power loss for your DMPPT when you design it to make it better than having two separate MPPTs. Does that make sense to any of you? This is like the constraint, the design constraint for designing the DMPPT to make it better than two separate MPPTs. Okay, and now we can see, like it makes sense in my head, but so let's see. So we transfer. Oh wait, and the total amount of power that we're transferring here is 50 watts, right? Because it's 1 amp 50 volt. We got 1 amp 50 volt. Yeah, we calculated that earlier. 50 watts. And we're allowed to use 8 watt or less to make it better than two MPPTs. So you only need an efficiency of 50 minus 8 divided by 50 is equal to
84%. Yep.
Okay. So if you like, that's not difficult, or at least and like in my world, it's not difficult to make a converter that's 84% efficient. Also, like it's not difficult to make a converter that's like 95% efficient or something like that. And that way you already have like 3 times less losses than having, like you have approximately like 2 watts of loss. It's already like a 6 watt power win compared to, so your DMPPT efficiency doesn't have to be that high to make it worthwhile. That's something I can tell. So like whatever, like basically whatever conversion you're able to make for the DMPT, it's going to be better than having two separate MPPTs if you control everything well. And with the boost converter circuit, it's even better, because here the power through the boost converter is only like 100 watts. You're allowed to lose 8 watts. Why is this better? No, because now you need like a 92% efficient converter. Well, which is still way less than the 99 of the MPPT, right? So like it makes a lot of sense to, like power wise, you're converting less power. So like, and like only a small portion of the power that you convert happens in the DMPPT. So it makes it worthwhile to make a system like this. Does that make any intuitive sense to you, to why a system like this would be more efficient than having two separate MPPTs? And that your efficiency of the DMPPT doesn't have to be that high to make it worthwhile? Hopefully. Any more questions? Like we're already out of time, aren't we? Oh no, we have 8 minutes left, and then the next presentation starts.
I have a quick question. So
Sav-
as
Savannah,
Oh,
Kenny, from what team are you?
yeah, I'm from Illinois State University Solar Car team.
Yep.
So
question?
as we prepare, obviously there's a lot of different technologies and things to consider when building our solar array. And so is there any other additional resources or things that you think we should be paying attention to as we continue that work and bring other students in so that we can like educate them? And really just like any kind of more general resources.
So your general question is like what person should we recruit in our team to take care of the solar array, or like how can I rephrase your question? Like
Yeah, it was more of just like, is there like, other than everything that we've kind of learned during your presentation, what are there other like websites or resources that you think we should take into consideration as we plan to build our solar array?
let's see, maybe someone else has answering your question on this, because we have a lot of people in the presentation. Does anyone else have suggestion for answering this question?
PV Education is a fantastic website and should absolutely be your best friend when trying to work with the array. So if you are not familiar with PV Education, I highly, highly recommend going and checking that out.
Yeah, no, I just looked it up. I am not super familiar with it. So thank you. That is awesome. I really appreciate it.
I realized I went into a lot of detail of super niche circuits that like maybe only 1 or 2 teams use right now.
I mean, that's what I was hoping to get out of this presentation.
Yeah,
So I'm
yeah,
happy.
but I'm not sure like if let's see what, maybe there's some more general things that are important as well. Like most teams make like some kind of weather model that calculates the position of the sun at every time of the day, and then they use that to calculate the amount of irradiation of each solar cell. And then they make expensive metals based on that, right? That's what most solar car teams do. I'm not sure if you can get any information on that somewhere.
Yeah, in the past, we've utilized that and like looked at what the race would be like to plan out how we would build our solar cells in our car. And so that is something that we take into account.
I'm trying to see if I have any advice on that. Does anyone else have extra advice on this to answer this question? Because I'm sure there's lots of stuff out there that I'm not aware of. Silence. Okay, any other questions then? I hope this answers your questions, Savannah. Because I'm not super familiar with all the research online. I usually do like I make everything up in my own head, usually.
That's
like any other questions about anything? Something else I wanted to say is that there are lots of different PPTs available on the market, and they all claim certain efficiencies. But what I've found from my own experiments is that like all manufacturers are really bad in measuring their own efficiency and putting it properly in their data sheet, because it's pretty hard to like measure like high efficiencies like 99% properly. If anyone needs help with this, I spent a lot of time, like half a year, on making like a really good setup to like do really, really good efficiency measurements. And I would be willing to like share that setup or like do measurements for other teams on efficiency of any kind of DC-DC converter. Or MPPT or anything that's DC-DC. Any other questions?
I do have another question. So if we were to reach out to you with questions or anything like that, what would be the best way for a team to get in contact with you? It's just your email that you presented at the beginning.
Yeah, email works. Also have LinkedIn, Facebook, WhatsApp. I can put my phone number. Most of you are American. I have an American phone number as well, which works. +1 415 644 8227. I'm just going to add some contact information in so you can screenshot it or something. For emails, that's the email address. LinkedIn, Facebook works as well. Just Google my name, Elmar Peters. Or, well, that works best for calls and texts. Yeah, that's it. I have a website as well that has some information on that might be useful. It's www.elmar.solar. Does that answer your question?
Yes, yeah, thank you.